we've seen example of phase diagram, what phase diagram looked like, right? So next we will look at the reactions in equilibrium phase diagram. And all of the phase diagram that we're going to look at, they are all binary phase diagram. Binary in this case refer to the components that we mix together, right? So like for example, this is a binary phase diagram of iron and carbon, right? This is a binary phase diagram of lead and tin, right? So we have only two components, which is lead and tin. In this case, we have only two components, which is iron and carbon. In this case, we mix them together, and it can produce many different phases, but the main components are just iron and carbon, right? And the main component in this system is just lead and tin, right? So this type of phase diagram is called a binary phase diagram. You can have a ternary phase diagram or a quaternary phase diagram when you mix two, or when you mix three or four elements together. But the ternary phase diagram looks really complicated. It looks like it is a three-dimensional phase diagram, so it's quite difficult to visualize. But the concept that you use in the binary phase diagram can also apply to those ternary phase diagram or quaternary phase diagram as well. So we're using binary phase diagram as an example for you to get the concept of phase equilibrium diagram, right? And then you can apply those concepts to other type of phase diagram. Okay, so in phase diagrams, there are different reactions that occur at equilibrium, right? And we'll look at different reactions, right? So in the first case, the phase diagram is called isomorphous phase diagram or binary isomorphous phase diagram when you don't have any reaction. Okay, when you don't have any reaction at all, it's called isomorphous. Iso, like from the Greek roots, iso means the same, right? And morph, from Greek root, means body or shape. So isomorphous means a phase diagram that you only have just one shape, one body, or one phase, right? There's only one phase that is present in that phase diagram. So you don't get any reaction or a three-phase invariant reaction, right? All these reactions are called three-phase invariant reaction because it involves three phases and it needs a specific composition and a specific temperature for these reaction to occur. That's why it's called invariant reaction, right? So it is a three-phase invariant reaction. The first one is called eutectic reaction. When you have liquid metal, upon cooling, that liquid metal or molten metal will turn into solid number 1 and solid number 2. Right? On the phase diagram, it will look something like this. You would get this point here where there are two lines coming down together. These two lines are called liquidus. We'll go into detail about these lines a bit later. But these two lines coming together, and these two lines will meet at this point here. And if you look at this point here, above this point, at a higher temperature than this point, you get just the liquid phase. And upon cooling down, that liquid phase will turn into solid 1 and solid 2, which is the alpha solid solution and the beta solid solution, which are both solid, right? So at this point here, you get a eutectic reaction. A peritectic reaction is when a liquid reacts with solid 1, turning into solid 2, right? So at this point here, you get liquid plus solid 1, which is alpha, turning into beta upon cooling, right? When you are cooling it down. In fact, all these reactions are reversible as well. So when you are heating it up, for example, alpha plus beta, when you heat it up, when you reach this temperature here, all the solid alpha plus beta will all turn into liquid. Right? Okay, so this is peritectic. Monotectic is one when you have a liquid number one turning into liquid number two and solid number one. Eutectoid is solid number one turning into solid number two and solid number three. And peritectoid is when you have solid number one react with solid number two to give you solid number three. Right? In metals, mostly we are concerning ourselves with isomorphous, eutectic, and eutectoid. Okay. It doesn't mean that there are no other reactions in the system that we want to look at, but the more important reactions are these reactions here: eutectic, eutectoid, and isomorphous. Okay, so well, for now you have to know that there are all these reactions, but there are three reactions that you have to understand, like how it happens, etc. Right? But you have to know that there are all these reactions. You might not have to be able to explain what happens during peritectic reaction, etc. Okay, and to make it a little bit easier for you, if you notice the eutectic reaction and eutectoid reaction, they are very similar, right? If you look at the phase diagram, you see that two lines coming down, those two lines meets, and below the point where the two lines meets, you have two phases, right? For eutectic reaction, you have the liquid phase turning into two new phases. For the eutectoid reaction, you have the gamma phase in this case turning into alpha plus beta phase. Right? So solid number one turning into solid number two and solid number three. Right? So it looks really similar. The only difference is that the eutectic reaction involves a liquid, whereas the eutectoid reaction doesn't involve any liquid at all. It's just a solid phase reaction. But if you look on the phase diagram, it looks almost exactly the same. Right? In fact, if you look at the peritectic and peritectoid reaction, you can say the same thing. Right? The peritectic reaction is the liquid react with a solid number one turning into solid number two. Right? But peritectoid reaction, it doesn't involve any solid. Right? So if the ending of the word is tic, T-I-C, whether eutectic, peritectic, or monotectic, please know that there's some liquid phase involved. But if the ending is toid, T-O-I-D, whether it's eutectoid or peritectoid, there's no liquid phase involved. Right? Well, we were looking at the phase diagram of iron before, right? And you can see that there are a few of these reactions in this phase diagram. Okay, so let's zoom in a little bit. Okay, so you can see that there are a few of these reactions on this phase diagram, right? And usually on these phase diagrams, when you have three-phase invariant reaction, you have a composition like marker around that area, and also an isothermal line, right? Isothermal line gives you the temperature for the reactions. So in this system, you can see that there are three reactions. There's one here, right? One here at 0.76% carbon at 727 degrees Celsius. There's another one here with 4.3% carbon and at 1147 degrees Celsius, and another one here at about 1493 degrees Celsius, right? So let's start with the one, with this one, with the one with higher temperature. What reaction happens at 1493 degrees Celsius? This reaction here. What reaction happened here, right? So sometimes the phase diagram, the phase view, the phase diagram is so small, so that they don't really like put in the symbol to tell you what are the phases that are present, right? If that is the case, you can fill in the blank yourself, right? For example, in this phase area here, right? This little triangle here, this triangle here, there's no symbol saying what phase is there, right? But we know that on the left-hand side of that triangle, we have the delta phase, right? In this area here, that's the delta phase, right? And on the left-hand side is the delta phase. On the right-hand side, we have the gamma phase. So we can probably guess that this little triangle here is the delta plus gamma phase, right? You can find delta and gamma in this condition here. And what about this bigger triangle here, right? So on the left-hand side, we have the delta phase. On the right-hand side, we have the liquid phase, right? So we can probably guess that this is the liquid plus delta, okay, in this area. So now we have the information that we need to say what is the reaction at 1493 degrees Celsius. So at this point, above this point, we have liquid plus delta, and below this point, we have gamma, right? So we have liquid plus solid number 1, liquid plus delta, turning into gamma, which is solid number 2. So this reaction is a what type of reaction? It's a peritectic reaction, right? We have liquid plus solid number 1 turning into solid number 2. Okay. Okay, so this is a peritectic reaction. What about here at 1147 degrees Celsius at 4.3% carbon at this point here. Above this point, we have the liquid phase. Below this point, we have gamma plus Fe3C, right? So above this point, we have the liquid phase, and below this point, we have solid 1 and solid 2, right? So liquid phase turning into solid 1 and solid 2, and that is the eutectic reaction, right? Liquid turning into solid 1 and solid 2. And if you look at this symbol, this representation of phase diagram here is exactly like that on the phase diagram, right? So you have these two lines, this line here and this line here coming down and join together at this point. And above that point, you get the liquid phase. Below that point, you get two solid phases. Right? This is the eutectic reaction. What about this one? At 727 degrees Celsius, above this point here, you get the gamma phase or austenite. Below this point, you get alpha plus Fe3C. Right? So a solid phase upon cooling turning into new solids number 2 and new solid number 3, right? So that is the eutectoid reaction, right? Gamma turning into alpha plus Fe3C, right? So in the as you can see in the iron carbon or in the steel phase diagram, we have eutectic, eutectoid, and peritectic, right? So and steel is the most widely used engineering material in the world. That's why we have to know a little bit about the eutectic reaction and eutectoid reaction, because they are the reactions that we find in the steel system, and that will affect the structure and property of steel, right? One of the most widely used engineering material. Okay, so when we have a phase diagram, there are three main objectives that you should be able to do, right? The first one is you should be able to describe the structural evolution and phase transformation during solidification or cooling, right? So what happens to an alloy of a specific composition? What happens to that alloy as it is cooling down from molten metal, from liquid metal? As it cools down, what phases are present and what are the microstructures that are present at each of the temperature as it cools down, right? So the structural evolution of phases, right? That is the first objective. And objective number 2 and number 3 are usually come together, right? So in fact, sometimes I would put like number 3 as like higher than number 2, right? So you should be able to determine the chemical composition of the two phases, well, or one phases or whatever, because first of all you have to know what happens, right? You have to know how many phases there are at each temperature, and then you have to be able to tell the chemical composition of each of the phases, whether it is just the one phase or two phase, three phase or whatever. You should be able to tell the chemical composition of each of these phases, and also you should be able to calculate or estimate the weight fraction or the amount of the phases that are present at that temperature. Okay, we will look at different type of phase diagram: isomorphous, eutectic, and eutectoid, and we will apply all these objectives to this phase diagram, right? The first one is the isomorphous phase diagram. We will look at the copper-nickel system, right? This is an isomorphous phase diagram. Like I mentioned earlier, isomorphous usually means there's only just one phase, right? Iso means the same, and morph means body or shape. So it doesn't matter how much copper or how much nickel you mix them together, you end up with the same shape, the same body, or the same phase, which is the alpha phase, right? The alpha phase is the solid solution, right? The alpha phase in this case is a solid solution between copper and nickel, and it doesn't matter how much nickel, how much copper. Either way, you would get just the alpha phase, right? You get a single phase, and you can see that the solubility depends on temperature, right? Okay, so we have the alpha phase here. For example, if we are looking at 35% nickel, 65% copper. Okay, so let's familiarize ourselves with the phase diagram first. On the y-axis, we have the temperature in degrees Celsius on the left-hand side, in degree Fahrenheit on the right-hand side. Right? On the x-axis, we have the composition or weight percent of nickel at the bottom here. On the top, we have the composition, atomic percent of nickel. Right, so we have both weight percent and atomic percent. And this is a copper-nickel system. So we have, when we have the weight percent nickel here, right? So we have 100% nickel on the right-hand side and 0% nickel on the left-hand side. Right? That means at 0% nickel, we have 100% copper, and at at 100% nickel, we have 0% copper, right? So on the left hand side, we have 100% copper. On the right hand side, we have 100% nickel. And what are these 2 points? This point here, this point here. Okay, so these 2 points are the melting points of pure copper and pure nickel, right? Because we have 100% copper here, and this is the point where solid phase turning into the liquid phase, right? Because we have liquid phase up here and we have solid phase down here. So this is where the solid phase turning into the liquid phase. So therefore, this is the melting point of copper, which is about 1085 degrees Celsius. Therefore, this is the melting points of nickel, which is about 1453 degrees Celsius. Okay, and you can notice that for pure metal like copper and nickel, there is a melting point or melting temperature, because that is the only temperature that melting occurs, right? So it starts at 1085 degrees Celsius for copper, and it finishes melting at this temperature. So there's a point, there's a temperature, that's the melting happens. The same thing happens with nickel as well. There's a temperature or there's a point where that reaction happens. But when you mix them together, copper and nickel, like 35% nickel, 65% copper, you don't get that melting point anymore. You have a melting range, right? So you have, say, if you have 35% nickel, 65% copper, and you heat it up from room temperature, it will start to melt at around 1210-20 degrees Celsius. It will start to melt. And when you get to about 1250 degrees Celsius, you get about, like, you get molten metal and a little bit of the solid phase still in there when you get to point B here, until you reach a temperature above this line here. Then you would get complete liquid metal or you complete molten metal, right? So what is this line here? This line is called a liquidus line. A liquidus line tells you that at a temperature above this line for any composition, you would get just the liquid, right? And this is the solidus line, the line below here. The solidus line tells you that at a temperature below the temperature of the solidus line at any given composition, you would get a solid phase, right? And you can notice that for pure nickel and pure copper, the liquidus line and solidus line becomes a single point. That means above this temperature you get molten metal or liquid metal, and below this temperature you get a solid phase, right? But for other composition, you get melting range. You get a temperature where it starts to melt, and then a temperature where it completely melts. And the same thing happens when you cool it down, right? When you cool down from liquid metal, it will start to solidify at the temperature of the liquidus line for that composition. For example, for 35% nickel and 65% copper, it will start to solidify here if you cool it down from high temperature, right? So it will start to solidify at about 1200 and maybe 70 degrees Celsius, and it will completely turn into solid at about 1210-20 degrees Celsius, right? So there's a range of temperature that you can find both liquid and solid together. Okay, and this is an isomorphous phase diagram because there's only one single solid solution phase, which is alpha in this case. It is a binary phase diagram because you only have two components. You have copper and nickel, right? So this is a binary isomorphous phase equilibrium diagram. Okay, to look at the objective one, right? The objective one is you should be able to tell or describe the microstructure evolution for any given composition, right? So let's take a look at our alloy of 35% nickel. This alloy here, right? What happens? Okay, at high temperature, it is just a liquid molten metal or liquid metal with 35% nickel. And as you cool down until it reaches the liquidus line, right? So from point A to point B here, when the temperature reaches the liquidus line or just a little bit lower than the liquidus line, you start to get nuclei of the alpha phase forming, right? You see nucleus forming, right? You get nucleation. Okay, so for phase transformation from liquid to solid, or in fact for phase transformation for any phase at all, there are two steps, right? The first step is called nucleation, when you get the nucleus forming, right? So as the temperature drops below the liquidus line from point A to point B, you start to get nuclei of the alpha phase. And then as the temperature drops further and further, you start to get more and more alpha phase, right? At point C, you get more alpha phase growing. At point E, you get more alpha phase growing, right? So this step is called growth, right? So there are two steps of phase transformation. The first step is nucleation. The second step is growth, right? So basically, you need a nucleus to form first, right? So when you have the nucleus, all the crystal will start to grow from those nucleus, right? So from nucleation, you start to get growth. And when the temperature drops below the solidus line, you get just the solid phase, right? So all the growth has finished, right? So now you get the solid phase only. Okay. Okay, so this is what happens, right? Okay, so at point A, we get liquid phase, 35% nickel, right? We start off with 35% nickel, the overall composition of 35% nickel. So at point A, we have 35% nickel. And when the temperature drops to point B, at the liquidus line or just below the liquidus line, we start to get nucleus forming. We start to get solid alpha nucleus, and we start to get, we still have some liquid there, right? And if we draw a tie line, this blue line here is called a tie line. A tie line is a line parallel to the x-axis, and it will intercept with phase boundaries. In this case, it intercepts with the liquidus line and solidus line. And when it intercepts with the liquidus line, it gives you the composition of the liquid phase. Right, so this tie line intercept with this line here, and it gives you 35%. And when it intercepts with the solidus line, it gives you the composition of the solid phase, which is 46% nickel. Right? Okay, so at this point, we have liquid phase and we have nucleus of alpha phase. And in the alpha phase, we have 46% nickel. The rest is copper. And in the liquid phase, we have 35% nickel. The rest is alpha. The rest is copper. But the amount of the alpha phase is so low that for now it can be neglected. Right? So some of you might be wondering, how come we have 46% nickel when we start off from 35, right? How come in the alpha phase we have 46%? But bear in mind that the alpha phase is just starting to form. There's so little alpha phase, so there's so little nickel in the alpha phase. So it can be neglected for now, right? But when we get to objective 2 and 3, you will see that the overall composition stays at 35%. Okay, but for now, we start to get the alpha phase. In the alpha phase, there's 46% nickel, but there's so little alpha phase, therefore there's so little nickel in there. Most of the nickels stay in the liquid phase, right? So that's why we have 35%. So if you want to be like completely and utterly correct, the liquid phase you would have about 34.99999% nickel, and in the alpha phase we would have 46% nickel. But because we have so little nickel, the amount of nickel multiplied by the fraction of the nickel in the alpha phase gives you that 0.00001% nickel that makes up 35%. Hopefully you will see that when we go to other objectives. Okay, so when we get to point C, which is between the liquidus line and solidus line, we have the liquid phase and we have the solid phase, right? When you draw a tie line to intercept the liquidus and solidus, you can see that in the liquid we have 32% nickel, in the solid we have 43% nickel. At point D, at the solidus, when we draw a tie line, in the liquid phase we get 24% nickel, in the solid phase we have 35% nickel, and at point D we have 35% nickel in the solid solution alpha. And as you can see from previous slide, as you cool down from the liquid phase, go down below the liquidus line at point B, you start to get liquid plus alpha. And then when you go down below the solidus line, you get like completely the alpha phase. And as you can see in the previous slide, the chemical composition of alpha and the chemical composition of the alpha of the liquid phase changes all the time during solidification, right? So you start off with the liquid phase having about 35% nickel, and then the liquid phase have about 32% nickel here, and the liquid phase has about 24% nickel here, right? 35 here, 32, 20, 24% nickel in the liquid phase. And in the solid phase, the alpha phase, you start to get 46% nickel at point B here. You have 43% nickel at point C here, and 35% nickel at point D here. So the composition of the liquid phase changes, composition of the alpha phase changes. Okay. Next, we will look at the weight fraction of the two phases at a given temperature, right? For the isomorphous system, the two phases are the liquid phase and the solid alpha phase. First of all, we have to apply the tie line to link between the two phases. So these blue lines here are tie line. So you take the temperature that you are interested in, you draw a tie line parallel to the x-axis. Say, for example, if you're interested in, say, 1280 degrees Celsius or 50 degrees Celsius, which is here, right? You draw a tie line here. The tie line will intercept with the liquidus and the solidus. And you can think of the length of the tie line as the overall amount of your material, right? So if the length of the tie line is the overall amount, or 100%, right, from from this point here to this point here is the 100% amount of your material, i.e., or in other words, the amount of liquid plus the amount of the solid alpha, right? The fraction on the tie line can gives you the amount of each of the phases. You can use the fractional length of the tie line to estimate the amount of each of the phases. But the overall amount is still 100% because each of the phases has a fraction of it, right? And when you combine those two phases together, you get 100%. Okay, for example, if you take this temperature here, temperature as point B here, you draw a tie line. You draw a tie line here, and the total length of the tie line represents the total amount of the material that you have, right? So in this case, the length of the tie line is from 35% nickel to 46% nickel. So the length of the tie line is 11 units, right? So in some phase diagram, you cannot see the number clearly. It doesn't matter. You can use a ruler to measure the length manually using a ruler, right? And the same concept still work. The fraction of the length represents the fraction amount of each of the phases. The total length of the tie line represents the overall, the total amount of the material that you have, right? So in this case, the number is quite clear, and you can see that the length of the tie line is 11 units, like from 35 to 46. Okay, so we can see that the liquid phase has about 11 units, and the solid phase has about 1 unit because it's exactly on the liquidus line, right? So now we have almost 100% liquid, right? We have just a little bit of the nucleus forming, and it's less than like 1%, less than 0.0001% even, right? So you have just a little bit. So we can say that that's 0% solid, 100% liquid at this point. But when the temperature drops further to temperature point C here, you do the same thing. You draw a tie line at point C here, right? You draw a tie line, and we can see that the overall length is 43 minus 32, which is 11 units. And we find that the liquid phase has 8 units, like the length on this side, and the alpha phase is 3 units, the length on this side, right? So 8 divided by 11 times 100 gives you 72.73%, right? So the weight fraction is the length for the liquid side, which is 8 units, divided by the total length, which is 11 units, right? That gives you 0.727, right? You multiply that by 100, gives you percent. So you get 72.73%. And you can do the same thing with the length for the for the solid side. Right, so you have 3 units here, right? Divided by 11 times 100 gets you 27.7%. Or you can just calculate this number here by calculate the length of the liquid side and take that out from 100. That will give you this as well, because the amount of the liquid phase and the amount of the solid phase must combine to make 100%, right? Okay. At point D, you can see that it's all solid, right? Because you have like 11 units. It's the overall or the total length of the tie line, right? 35 minus 24 is 11 units. The total length for the liquid side is 0. Total length for the solid side is 11 units. So we have 100% solid. Okay, so you might be wondering which side represent the solid, which side represent the liquid, right? But if you look at the tie lines, look at each of these tie lines. If you look at this tie line, right, you can think of your point of interest as the dividing point of the tie line, right? And you see this tie line here, the right hand side of the tie line will get shorter and shorter as the temperature decreases, right? So in this picture, the right hand side takes up about almost 100% of the tie line. In this tie line, you have this length, and at this point here, the right hand side is almost like 0. And we know that the fractional length of the tie line represent the different phases, right? And what phases that you have a lot of in the beginning, and as the temperature cools down, you see the length is getting shorter, so you have less of that phase, and getting less and less and less until you get to that point, that length becomes 0, right? So, what phase should be represented by the right hand side of the tie line? In this picture, you start off with a lot of it, and when you cool down a little bit further, the right hand side getting shorter. And if you draw another line here, another temperature and another line here, you can see that the tie line on the right hand side is getting shorter than before, right? So you can say that the phases that is represented by the right hand side is getting less and less and less, and that phase is the liquid phase, right? As you cool down, you get less and less and less liquid. And the left hand side of the tie line is getting longer, like from zero length here, gets a little bit longer here, gets a little bit longer here, and we get to about 100% of the length of the tie line here. And what phase gets more and more and more as temperature decreases? That's the solid phase, right? So you can draw a tie line and you can try to work it out instead of just like memorizing which side of the tie line or which side of the dash line is your like solid, which side is a liquid phase. Okay, so now we can estimate the amount of each of the phases, and we can sort of tell the composition of each of the phases as well, right? We can tell the composition of each of the phases as well, right? By looking at the intersection of the tie line, right? So from previous slide, like from this slide here, when you draw a tie line, you get the intercept of the tie line with the liquidus and the solidus, and the intersection with the liquidus gives you the composition of the liquid, right? So it intercepts the liquidus here, so it tells you that the liquid has 35% nickel. It intersects the solidus here, so it tells you that the solid phase, the alpha phase, has 46%, right? So from the intersection, you drop a line down here, and you can read off the x-axis, and you can see that it is 46% nickel for the solidus line. And as the temperature drops further, the composition of the liquid changes, and the composition of the solid also changes. In fact, the composition of the solid and the composition of the liquid changes along the liquidus line and along the solidus line, right? Okay, the chemical composition of the liquid was altered or changed during solidification following the liquidus line, right? So you start off with 35% nickel, and then a short time later, in the liquid phase, you have 32% nickel, and a short time later, at a lower temperature, in the liquid phase, you have 24% nickel, right? So you can see that the composition of the liquid phase follows the liquidus line. And the composition of the solid phase also follows the solidus line in the same fashion, right? So you start off with the solid phase has about 46% nickel, and then the composition of the solid phase changes along the solidus until you get to 35% nickel, right? So during solidification, you start off with the overall composition of 35% nickel, and the amount of nickel in liquid changes, the amount of the nickel in solid changes, but the overall amount, you start off with 35% nickel, you end up with overall amount of 35% nickel in the solid at like this temperature here, right? Okay, so even though the composition of the liquid changes with temperature, composition of the solid changes with the temperature, but in the end you end up with the same overall composition, right? Okay, but why is that? Why do you have the same overall composition? Okay, think about it. At this point here, at point B, right? At point B, we have liquid and alpha, right? And in alpha, we have 46% nickel, and in liquid, we have 35% nickel, right? But at point B, we have almost 0%, alpha, very, very little amount of alpha. Even though in that alpha we have 46% nickel, right? That means the total amount of nickel in alpha is negligible, like really, really small amount. And most of the nickel is still in the liquid phase, right? And we have a lot of the liquid phase. And when we get to temperature C here, you can see that there's 72% liquid, right? And in those 22%, well, the amount of liquid is 22%. And in that liquid, we have 32% nickel, right? So imagine we have 100 kilogram of our alloy. At this temperature, 72% is still in the liquid phase, and 27% is the solid phase, alpha, right? So if we start off with 100 kilogram, we have 27 kilogram as a solid alpha, and 72 kilogram as the liquid phase. And in that 72 kilogram, 32% of that is nickel, right? And in that solid phase of 27 kilogram, about 43% of that is nickel, right? So you can find the total amounts of nickel, right? The total amount of nickel to start with in 100 kilogram alloy, we have 35 kilogram of nickel, mixing with 65 kilogram of copper, right? So if you take 32%, multiply that by 72 kilograms, you get the amount of nickel in the liquid phase. And if you take 27 kilograms multiplied by 43% nickel, you get the amount of nickel in the solid phase. And you take those two numbers together, that makes up 35%, 35 kilograms of nickel, right? Okay. Um, okay. Uh, 32. Okay, so you can try to um, calculate that in your own time. You will see that total the total amount of nickel stay the same throughout, right? The total amount of nickel stay 35%, right? So you can see that there's in the solid phase there's more nickel in copper, but there's so little solid phase at this point here, right? There's only 27% solid, and in that solid there's more nickel than that's more nickel than the overall composition. But when you are taking average of the total amount of nickel, it still stays 35%, right? um okay, so okay, another take home message that I want you to take is that the composition of the phases changes as the temperature changes, right? The composition of the liquid phase changes along the liquidus line, and the composition of the solid phase changes along the solidus line, right? So for isomorphous phase diagram, maybe that doesn't mean anything much, but when we are looking at the eutectic phase diagram and eutectoid phase diagram, that will mean a lot more, right? What happens uh, when the temperature drops and the composition changes? Okay, that will mean a lot more, and that is the topic that we are going to cover next week.